Welcome to this video on Introduction to Vectors. Before we get to the lecture, I would like to draw your attention to two other resources. A textbook that is available on Amazon and a software that is available at this website. At the end of this presentation, you should be able to write a vector in its component form, determine the unit vector from the components of a vector, determine the direction cosines of a vector, and write a vector from its magnitude and direction cosines and add two vectors. Vector definition. Vectors are quantities with magnitude and direction. Examples of vector are velocity, acceleration, force, and moment. Pressure, temperature, volume are not vectors. Here is two examples of a vector. We have chosen four directions: east, west, north, and south. This is a velocity vector of 35 feet per second, which makes an angle of 60 degrees with the south. This is an acceleration vector, which makes an angle of 30 degrees to the west. This is a force vector, which is applied at this joint of a structure, which makes an angle of 60 degrees to the downward direction. This is a moment vector shown on a screwdriver. When you turn the screwdriver clockwise, the moment vector is pointed towards the tip of the screwdriver. You must draw or define a vector in a right-handed Cartesian coordinate system, which is shown here. Curl four fingers, and the curl direction of your four fingers is from X to Y, and then the Z direction is pointed towards your thumb. So here is a position vector drawn in the XY coordinate system. The coordinate of this point is 3, 2, 3 along x-axis and 2 along y-axis, which means that from the origin you take 3 steps along the positive x-axis and 2 steps along the positive y-axis. 1 step along the positive x-axis is the x unit vector, and 1 step along the positive y-axis is the y unit vector. Therefore, the position of this point is described by the vector 3x unit vector plus 2y unit vector. Similarly, the coordinate of this point is -6 along x-axis and positive 1.5 along y-axis. So you take 6 steps along negative x-axis and 1.5 steps along the positive y-axis. X unit vector, y unit vector, they define 1 step along the x-axis and 1 step along the y-axis. So the position vector is -6x plus 1.5y. Here is another position vector where the coordinate of this point is -2, -8, and the position vector of this point is -2x, -8y. Coordinate of the point is 2, -8. The position vector is 2x minus 8y. Here is a vector shown in 2 dimensions. The vector is A. It has 2 components, ax and ay. Ax is along the positive x-axis, AY is along the positive y-axis. So the vector A is AX x unit vector plus AY y unit vector. The magnitude can be calculated by using the Pythagoras theorem, where magnitude of A is along the hypotenuse, so it's base square AX square plus height square AY square. So magnitude of A is AX square plus AY square. The unit vector is a vector along A, but that has a length of 1. So the unit vector is A vector divided by the magnitude of A, but A vector is AX x unit vector and AY y unit vector, and so we divide this quantity by A and A. The magnitude of the unit vector is 1, which you can prove. Magnitude of unit vector is the square of its x component plus the square of its y component, and if you simplify that, you will get magnitude of the unit vector equals 1. Now let's talk about direction cosines. Again, we show the A vector, which makes an angle of theta x with the positive x-axis, an angle of theta y with the positive y-axis. From this right angle triangle, we can see that AX divided by A is cosine of theta x, and AY divided by A is cosine of theta y. Cosine of theta x and cosine of theta y are the direction cosines. You can write the unit vector in terms of the direction cosines, as unit vector of A is direction cosine with the x-axis multiplied by the x unit vector, cosine of theta y multiplied by the y unit vector. One thing that you will have to remember is that theta x is the angle between the vector and the positive x-axis. Theta y is the angle between the vector and the positive y-axis. The direction cosines are not independent. As we know, unit vector of A is cosine of theta x, x unit vector plus cosine of theta y unit vector, and magnitude of the unit vector is 1. Therefore, cosine square theta x plus cosine square theta y equals 1. This is a very important equation that you must remember, that the angle theta x and angle theta y, they are not independent. Now let's talk about a direction cosines a little bit more. Why direction cosine? Why not direction sine? Because the cosine function has a very important property. As we have talked about before, the x direction cosine is cosine of the angle between a vector and the positive x-axis. It does not matter whether you measure this angle in a clockwise or counterclockwise sense. So this theta x you can measure clockwise or counterclockwise. So the x component of vectors in the diagram are, for this vector of magnitude 5, we can write it in two ways. The angle between the vector and the positive x-axis is either 70 degrees is either 70 degrees, or if you measure it, 70 degrees in a counterclockwise sense, in a clockwise sense, or 290 degrees in a counterclockwise sense. As it doesn't matter whether you measure the angle clockwise or counterclockwise, you can write the x component of this vector as 5 cosine 70 or 5 cosine 290. And the same thing holds true for the vector of magnitude 9. The clockwise angle between the vector and the x-axis is 160, and the counterclockwise angle between the vector and the x-axis is 200. So you can write the vector in two different ways. Similarly, for this vector of magnitude 8 and for this magnitude of 6. Same thing happens for the y component. You have to measure the angle between the vector and the positive y-axis, and you can measure it either clockwise or counterclockwise. The y component of the vector of magnitude 5 measuring counterclockwise is 5 cosine 20, or clockwise as 5 cosine 340. You can convince yourself that the remaining vectors are the y component of all of these vectors are written in two forms. One where we measure the angle either clockwise or counterclockwise. It does not make any difference. Now let's say I have given you a vector, but I have not given you the direction cosines directly, but I'm showing a triangle AB with this angle alpha. How will you find the direction cosines here? Alpha is tan inverse A over B. So the angle between the vector and the positive x-axis, the counterclockwise angle between the vector and the positive x-axis is pi minus alpha, and the angle between the vector and the positive y-axis is pi by 2 minus alpha. So we can write the x component as f cosine pi minus alpha, which is theta x, and we can write fy is f cosine pi by 2 minus alpha, which is theta y. And in this situation, what we do is find the angle beta. Now, the angle between the vector and the x-axis is, as you can verify, pi minus beta, measuring in counterclockwise sense, and theta y, that is the angle between the vector and the positive y-axis, is this measured in the clockwise sense. So we can write the components as fx equals f cosine pi minus beta. Pi minus beta is theta x, or we can write f cosine pi by 2 plus beta, where pi by 2 plus beta is theta y. Vector addition by components determining the resultant. Let's say we have a vector. A has two components, ax and ay. B has two components, bx and by. So you first draw the A vector with components ax plus ay. And if you want to add A and B, what you have to do is put the tail of the B vector at the tip of the A vector and draw the B vector with components bx and by. And now the sum of the two vectors A and B is from the origin all the way up to this tip, and as you can see from this diagram, the y component of the sum of these two vectors is ax plus bx, and the sum of the y components is ay plus by. What if you have another vector, c, with components cx and cy? You can find the resultant r as a plus b plus c, which is ax plus bx plus cx, and ay plus by plus cy. And this is the drawing for that. Here is a vector. We have put the tail of the b vector at the tip of the a vector, and then for the third vector c, we put the tail of c vector at the tip of b vector, and then this vector becomes a plus b plus c. Let's work out some problems. Find the resultant and the angle between the resultant and the x-axis and y-axis. So if I want to write the expression for the resultant, first I have to write these two vectors in component form. So for the 2000 Newton force, the angle between the force and the positive x-axis is 30 degrees. The angle between the 2000 Newton force and the positive y-axis is 60 degrees. So we write F2k as 2000 cosine 30 and 2000 cosine 60, and we get these as the components of the 2000 Newton force vector. We have to slide the 600 Newton force downward, because you remember that we have to put the tip and tail together. So we slide the 6000 Newton force, and now we can add this vector and that vector. When you slide a vector along its line of action, the vector does not change. So alpha is tan inverse 4/3, which is 53 degrees. The 6000 force makes an angle of 53 degrees with the x-axis and 53 degrees plus 90 degrees, which is 143 degrees with the y-axis. So we can write the 6000 Newton force in its vector form. And then we add the two vectors, and we get this. And the magnitude of the resultant is sum of the squares of the components, and then you take a square root. So we get 6552 Newton. To find the angle between the resultant and the x-axis and y-axis, the angle between the resultant and the positive x-axis is cosine inverse 53.43, which is the x component, divided by 6552, which is the magnitude, and we get the angle as 35.4. Similarly, we calculate the angle between the resultant and the positive y-axis. Find the angle theta so that the resultant is this. So we know this force and its direction cosines from this triangle. We know this force, but we do not know the direction cosines for the 2000 Newton force. However, we can still write the 2000 Newton force in vector form. The angle between the 2000 Newton force and the x-axis is theta x, and the angle between the 2000 Newton force and the y-axis is pi by 2 minus theta. So we can write the 2000 Newton force in a vector form like this. As before, we slide this 6,000 Newton force. Alpha is 53, 6,000 Newton force, we get the vector form. We add these two vectors to find R, which is F2k plus F6k. F2k is the unknown vector because of the unknown angle theta sitting in here and here. So we write F2k as R minus F6k. R is given here. F6k we calculated here, so we can find F2k as this. But we also know that F2k is this from here. So we find 2000 cosine theta is 1339, and 2000 sine theta is 2792. When we have this, divide one equation by the other, you will get tan theta as 2792 divided by 1389, so theta is 63.5. Find the length of the rod PQ and the unit vector along PQ. Vector OP, which means you are walking from origin O to P. For that, you will have to walk 3 feet along x-axis and 2 feet along y-axis. So OP is 3i plus 2j. Now we find the vector OQ. To find vector OQ, you have to walk from O to Q. For that, you will have to walk 4 feet along y-axis and 6 feet along z-axis. So the vector OQ is 4j plus 6k. But when you go from O to P and then P to Q, so you're going from O to P and P to Q, you have effectively gone from O to Q. So that is the vector addition principle, which means PQ is OQ minus OP. We know OQ and OP, so we can find PQ as this. We can find the magnitude of PQ by squaring all the components and adding them and then taking a square root, and so we get the length of the vector PQ as 7 feet. And the unit vector along PQ is the PQ vector, which is here. Divide that by PQ, which is the magnitude, which is 7 feet, and you get that as the unit vector of PQ. Long way of calculation by using Pythagoras theorem would with this, and I believe that the vector calculation is much easier. Thank you.